So, in today's lecture, we continue our discussion on continuous countercurrent multi-stage extractors. If you recall, in the previous class, we said that if you fix the amount of solvents, then the number of stages will be fewer, or if you fix the number of stages, then the amount of solvent required will be lesser in continuous countercurrent stages than cross current stages. So, in the earlier class also we had this equilibrium diagram, and we marked all the salient coordinates of different streams. On cross current extractors, there the approach was look for a mixing point. So, we have one stage where the fresh solvent comes in contact with the feed, so we get a mixing point. Then we have this equilibrium between extract and raffinate. Then the raffinate is taken to the second stage where the solvent is added. Then we have again equilibrium between the raffinate and the extract, two living stages. So, the mixing points keeps on changing, and we track that mixing point, find the tie line which goes through the mixing point, signifying the two living streams, extract and raffinate, they are in the equilibrium. In case of countercurrent multi-stage reactors, we have the feed here and we have the solvent at the end, and the two streams, they don't see each other. And similarly, the two living streams, the raffinate and the extract, they do not see each other. So, they are not in equilibrium. Otherwise, in every stages we do have two streams living, they are in the equilibrium. If it's an ideal stage. So, the approach to solving the problems related to continuous countercurrent multi-stage extractor is to locate difference points, del points. This is also very similar to the approach we had in case of distillations, where we located del D for the rectifying sections and del B for the stripping sections. So, here we said that in case of continuous countercurrent multi-stage contactors, the flow rates between the extract and the raffinate at any stage is a constant. Difference between the two is a constant. So, we locate for the del D points, and then we draw the different operating curves. All right. So, based on the same approach, here we will like to determine what is the minimum amount of solvent when the operating line becomes parallel to the tie line. That will give us infinite number of stages. So, then from the operation point of view, we have to choose the solvent or the amount of solvent in excess of this minimum amount of solvent. All right. So, let us start this new topic today, which is how to determine the minimum amount of solvent in continuous countercurrent extract. So, we are continuing our discussion on continuous countercurrent multi-stage contactor or extractor. All right, and we can make a note here that this gives fewer number of stages for a given amount of solvent, or vice versa. All right, we'll come back and take this example on continuous countercurrent multi-stage extractor and cross current extractor later in the class. All right. So, what is the approach here? Suppose we have, say, several stages, the cascade. So, feed enters from the left. So, we have F, XF, and let us say we have this general stages here, S, and then we have at the end the last stage, which is NP. So, the raffinate leaves with the molar flow rate RNP with the composition XNP. So, we have the feed enters here. So, in continuous countercurrent, we have the solvent entering from the other end. Say the mole fraction of the solute is very small, let us see, it is YS. So, we have this type of situation, and then the solvent or extract phase leaves at the stage 1. So we have E1, Y1. Here we have now R1 and this is E2. So same conventions, 1 goes with the 1 and 2. This stream originates from the stage 2. So we have 2 here. So this is S here, which means this would be RS, excess. And here we have ES plus 1, YS plus 1. Similarly, this should be ENP, YNP, and here we have RNP minus 1. So this is what we have here. And we want to find out what is the minimum amount of solvent. So this is the amount of solvent which will give us infinite number of stages. So that means the amount of solvent required will be larger than S minimum. So first we have to determine how much amount kg per hour of S min is required, which gives us infinite number of stages. And here we are saying that operating line coincides with equilibrium line or tie line. All right. So the driving force of a mass transfer becomes 0. We have infinite number of stages, and then we calculate this minimum number of stages, and we choose in general say 1.2 times or 1.5 times S minimum. Okay. And again here, if following these conventions, we have this tie line or equilibrium line which connects YS versus XS. So if this is XS here, this is YS, two streams are in equilibrium. We are considering ideal stages. So tie lines connects, or equation for the tie line connects YS versus XS, and we have the same convention for the operating line. We have YS plus 1 versus XS. So YS plus 1 is here, YS is here. So we have YS plus 1, which would be next stage here. So that would be, say, let's say YS plus 1. If you excuse me. So we're going counting from this side 1, 2, 3. We have this stream here is YS plus 1, and we have this XS operating line connects between YS plus 1 and XS. So we have the similar conventions which we followed in case of distillation stages also. If you have the stage number n here, the living streams has Yn, Xn, and here we have Yn plus 1, capital N here, Yn plus 1, if you are counting from the top to the bottom. All right. So similarly, this is the liquid which comes here is Xn minus 1. All right. So now let's come down to this equilibrium curve here, and let's see how do we address the minimum amount of solvent required. So this is A feed, B is a solvent, and C is the solute. And let's see if we have the equilibrium curve like this. Okay. Now in general, the feed composition is fixed here. So we have F and we have XF denoted by this coordinate here. And let's say that solvent is nearly pure. So we have S and we have this YS. Okay. So generally it happens that the first feed is given here. We have been asked to treat this feed. So right, the feed composition is XF, and we have been asked to reduce the concentration from XF to the last stage NP, which is XNP here. To do that, we have been given this solvent with the composition YS. So in general, F, XF, XNP and YS they are given, and we have been asked to find out how much is the amount kg per hour of solvent required to bring down the level from XF to XNP. So here, corresponding to XNP, very small amount of solute in the treated raffinate, we have, let's say, mark this location as RNP with the mole fraction XNP. So in general, you will see that most of the times F, these three coordinates, they are fixed here. All right. So now if you have F and S, if we connect, then we can have somewhere here mixing M coordinate as a m. So let's say that we have some coordinate m. Okay, so this represents the combination or mixing of f and s. And now, since we know the raffinate coordinate here, we can connect this to obtain this E1. So this would be E1. So now notice this, that the two streams E1 here and raffinate RNP, they are mile apart. They are not in equilibrium. At every stage, the two living streams, raffinate and extract, they are in equilibrium. But here, this is the first stage and this is the last stage. All we have done, we have connected this, we have made an overall material balance, and we have located this M point, and then we have, knowing this RNP, we extend this, connect this to make a intersection at this equilibrium curve at point E1. Then E1, the stream here, the first stage 1, this is R1, and here we have this E1. So these two streams are in equilibrium. What we did here, that we can find this tie line to obtain this R1. But then to proceed further, what we did in the last class, that we realized that the difference between two stages. So here we have stage 1, stage 2. The difference between the flow rate of these two streams is a constant. So essentially we are saying that F plus S equals R1 or RNP plus E1, and at the same time we can write like F minus E1 equals RNP minus S1. So that if we extend these two lines, F and E1, and we extend this line here, then they will intersect at a point, we call it del D, difference point. So between any two stages in continuous counter current stages, we have this difference point here. Once we know this difference point, we can proceed further. We have E1, this is stage E1 in equilibrium with R1. We extend, connect this R1, extend here. We have E2, E2, and again in equilibrium with some stream here R2. We connect this and we extend here E3. So we have R1, then we have this R2. So the idea here is very similar to what we had in case of distillation column. We located del D points and del W points because the molar flow rates between the two streams arriving and leaving is a constant and given to the equal to the top product molar flow rates or the bottom molar product, okay, molar flow rate. So we have the similar approach here, realizing that the difference between the raffinate and extract, stage 1 or stage 2 or stage S, anywhere it's a constant difference between the two, we locate this difference points. And once we know the difference points, we can have this operating line and we can have this tie lines, we can proceed. Now to determine the minimum amount of solvent, we have to see that what is the condition when the operating line, which originates from del D and intersects the equilibrium curve, becomes parallel to this tie lines, or it coincides with the tie line. So when it coincides with the tie line, that time the driving force, or that stage, driving force for mass transfer is 0, and we require minimum amount of, we require infinite number of stages for the separations. So we locate that del D min, then we take the operating point, which is 1.2 times or 1.5 times. All right. So to address this, to determine what is the minimum amount of solvent required, let's see what is the locus of this del D as we vary the amount of the solvent. So let's redraw this equilibrium curve and see how does this del point moves or changes as we increase the amount of the solvent. So we say that let's fix F. We know this R and P, it's given to us, and we have been given, and the quality of this solvent is fixed here, which is given as S. So we connect this Fs, overall material balance, to begin with. We know this M, we connect this to get this E1 here. We extend F and E1, we extend F and R and P and S. We have this del R. Let's say R denotes for raffinate here. Now, if we increase the amount of solvent, so let's notice, so this point is fixed here, this point is fixed here, this coordinate is fixed here. All we are doing is we are increasing the amount of solvent. If we increase the amount of solvent, then you can make out that this point will move towards this. All right. So this mixing point will move here. Then if we extend the second, suppose the mixing point has moved from here to here, then we get new E1, let's say E1 prime, and now if we connect this E1 and F1, then you can make a notice that this del R point is going to move further down. Let's say it makes connections here at different locations del R1, right. If we decrease the amount of solvent, then this M is going to move further here. Then if we connect this raffinate, you get another E1 prime, and now if we connect this F1, this point is going to move in this directions, del R double prime. So we make a note that increasing the amount of solvent results in the movement of difference point del R away from R and P. So when we increase, this del R points moves in this directions. So if we just, let's say, just locate S here, and let's say this R and P, and let's see this is your del R. So this point is fixed, this point is fixed here, we can extend this line here, and if the amount of S increases, del R moves in this directions. What happens if we keep on increasing the amount of S? Ultimately, this line which connects extract E and F will become parallel to this line which connects S and RP. So we also make a note that increasing amount of solvent may result in the line E dash del R. So the line which connects extract and del R may result in the line parallel to line del R and S. All right. So you should make a note here that if you increase the amount of solvent, if you are increasing the amount of solvent, del R moves in this directions. If S decreases, all right, then del R moves in this directions. If you keep on further increasing, there is a stage where this extract, okay, let's redraw here. So we have A, we have B, we have C, this extract, this equilibrium curve here. We say the point F is fixed, we have S fixed here, we have R and P fixed here. And if we keep on, and this is a line which extends in this directions. If we keep on increasing the amount of solvent, then E1 extract, this will move in this directions. So S goes this in this direction, E will go in this directions, and the line connecting this E to F, which gives us del R, moves in this directions. Till we keep on further increasing, this line E, extract, F and del R will become parallel to this line. So there will be a stage where we have this S, R and P, and then very far from here is it possible that this line which we have connected is now parallel to this. If we further increase the amount of S, then we said that this del R now will appear on the right hand side. In other words, if we have the equilibrium curve, let's redraw A, B, C, and we have the same equilibrium curve here. The point F is fixed, the amount of raffinate R and P is fixed, this solvent S is fixed. If we keep on increasing the solvent, then now the line which connects F and E will move in this directions. So if we have R and P, and now we have the solvent here, now this point is going to move in this direction. So we will have the del R appearing on the right hand side. So it's very important that we understand the locus of this del R points here. At a certain amount of solvent, if del R is on the left hand side, like in this case here, we increase the amount of solvent till this line becomes parallel to this, right? Keeps on moving in this direction till it becomes parallel to this. We further increase, now the line appears on this right hand side difference. So we have now this F and A. Now let's see what is the conditions when the operating line becomes parallel to the equilibrium curve. All right. So before this, let's just try to summarize here that we have been able to locate the locus of this del points as the amount of solvent is increased. Okay. So to start with, if we have the feed composition is given to us, raffinate composition is given to us, and the solvent composition or the quality is fixed to us. We are only changing the amount of the solvent. So if the difference point lies here, that means F, E extract, the intersects, the line connecting F and E intersects R and solvent on the left hand side of the curve, and then we further increase the amount of solvent. This point will move till this line becomes parallel to this. Further increase, now the difference point appears on the right hand sides. In this case, now the slope of the operating curve has changed. Earlier it was on the inclined in this directions, now it has changed in the other directions. All right. Now with this, we should be able to find out under what conditions these operating lines, either this way or this way, becomes or coincides with the tie line. That will give us the minimum amount of solvent. If we can locate del R min, then we can take 1.2 times or 1.5 times the amount of solvent. All right. So now here also there are two cases. Okay, we will consider case 1 when the equilibrium or the tie lines have the slopes very parallel or slopes nearly same as the operating lines. Okay, so there are two cases here. So we have A, B, C, and this equilibrium curve here. Let's say this is a feed. This is R and P. And here we have this S, and let's say del R points passing through this, okay, is here. So this is E1. Now there is a possibility, and there are several such tie lines. So these are the equilibrium curves. So let's say that equilibrium curves, the slope of the equilibrium curve is like this. All right. So the way we did in case of distillations, let us to find out what is that del min, or right, which corresponds to the operating line, which we have drawn in the previous cases, several cases like this, becomes or coincides with this tie lines. So the first thing is that find out that tie line which extended will pass through this or intersects this R and PS. In other words, to find out the del R min in this case, all we have to do is, if we have curve like this and this is F here, what we have located S, we have located R and P, and we have extended this line here. We are looking for del min. What is the minimum amount of solvent when the operating line becomes coincides with the tie line. So all we do, we find that tie line in this case, which if we extend will intersect the point line here. So you can say that now we have the amount of solvent corresponding to this del min, which will give us infinite number of stages, because now this is the same operating line which is now coinciding with this tie line. All right. So there are several such tie lines. First, what we should do, find that tie line, the first tie line, which if we extend, it intersects the line connecting between R and P and S to give us del L min. Once we locate this del L min, our definition for solvent, we can apply a lever rule along this line. S, all right, divided by R and P, amount of solvent per amount of this raffinate will be equal to del R, which is del R min here, dash R and P. So the segments to S over R and P is the segment del R RNP. So this segment divided by RNP, so we have the total segment del R min. Yes. So the bigger segment from here to here. All right. So from here, once we locate this point, we can calculate S minimum. Then we can choose S as 1.2 times or 1.5 times S minimum. All right. Now, if we choose any amount of solvent greater than S min, you recall just in a previous discussion, now the operating curve will move further away. And if it goes to that extent that del operating point has come to the right hand side, then we can also have operating line right here. In this case, all the operating line will originate from here, and in no way any of these operating lines will be coinciding with any of these tie lines. Now there is one more important thing here, that there is a possibility that some of the tie lines underneath this first tie line, which crosses through F, can give del min larger than what we are getting right now. So let's try to take this a special case. There is also a possibility that we have equilibrium curve, and this is F here. We have marked RNP, we have marked S, we have extended this line here. This is a tie line which extends through F, and it meets difference point, or it meets this line right here. Now we said that in general it's possible that all the tie lines, they will be, if you extend, then they will be intersecting this line closer to this RN, like this. But in some system it's possible that certain tie lines are like this, which means if you extend, then this will be intersecting this line or this curve further away from this RNP. So in these cases we must choose that intersections, that del difference which is farthest away from RNP. In other words, one is supposed to extend all the tie lines which intersects with this line connecting this RNP and B further away, the furthest away from this RNP. So we also make a note of this. In general, of course, we said that all tie lines, if you extend, then it's possible that the first tie line which crosses this F will give us the minimum del min. But there are several different type of systems where we have this type of situation that tie lines need not be like this. Some of the tie lines may be like this, which can be extended to give us del min farthest away from this RNP. All right. So based on this, then we should calculate S min. All right. So okay. All right. So this is also very similar to what we had in case of distillation. If you recall, we had equilibrium curve HV, HL, and we said to find out this minimum amount of reflux ratios, if this is a location for feed, then find that tie line which extend here. This gives us R min, and then there is a possibility that in certain system, non-ideal systems, certain other tie lines which you extend will give you R min. So we have also similar kind of situation in case of extractions. So one has to do some inspections to find out the minimum amount of solvent. Similarly, if we have the tie lines, say case 2, where the tie lines are downward in the other direction. So if you have the tie lines like this, in this case also one has to extend. So if you have this RNP and YS, if you extend like this and this, so in this case you can make out that the tie line which passes through F, if you extend, this will give us del min. And if you choose the amount of solvent greater than this S min corresponding to this del min, then the del point will move further towards this RNP. All right. So in this case also, the amount of S min for given amount of RNP, the definition will remain the same. S min over RNP will be tie line the segments connecting R and P and this YS or S over del min as S. So the definition is the same. From this we calculate S min and then take S as 1.2 times or 1.5 times S min, alright, and then that will give us new del. And then if you increase this any amount of solvent in greater than this del, of course never this operating line will be parallel or will coincide with any of the tie lines. Okay, so that's the discussions we had. We just want to summarize here one more time with this equilibrium curve. It's all about the locus of this del points, and we have two types of situations. Either the tie lines are like this or tie lines are like this. We have to find out the amount of solvent which coincides with any of the tie lines, which gives the minimum amount of solvent, and then take 1.2 or 1.5 times to be in the safer sides. So here if we fix this R and P and connect this S, this can go either way. To locate this F, find this tie line which you extend to give del min. Alright, if the tie lines are downward, then find that tie line which you extend in this directions. This will give you del min this way. So depending upon what type of systems we have, we'll get del min here, del min here. More important is that if you take larger any del greater than this del min, then del operating will move in this directions, and if you choose del greater than del min, then your del operating will move in this directions. Alright, so depending upon what type of systems we have, one has to inspect the type of equilibrium curve and then locate this del L min, either here in this case or in this case. Alright, so that's the discussion we had for total amount of solvent. We will of course take an example in this case to locate this del L min, which corresponds to minimum amount of solvent required. And we said that it all depends upon the slope of this tie lines. In some cases extract equilibrium composition is greater than this raffinate, so we have upward slope. In some cases we have extract compositions smaller than the raffinate, so we have the downward slope like this, and del min can move from the left and the right hand side. On the other hand, as far as the amount of solvent is concerned, if we keep on increasing and if we start with certain difference point is going to move further away from the raffinate till the line becomes parallel to this. Del operating moves to the right hand sides. Further increase, it will move towards R and P. So the locations of this del points is like clockwise with the increasing amount of the solvent. Equilibrium lines, thermodynamic lines, that depends upon your type of the systems which you have. If you have a tie line like this and your operating line is on the right hand side, then you are on the safe side. You don't have to worry about any of that operating line coinciding with this tie lines. But if you have del points on the left hand side and you have the tie line also in that direction, then there is a risk of operating line becoming or coinciding with this tie line. In that case, first find the del min, take 1.2 or 1.5 times, and then increase your solvent amount. All right. So now we take an example. Now we have, if you recall, we have taken three cases. One was single stage extractor. Then we talked about cross current stages. So we have 1, 2, 3, 4 stages, but we had this cross current. And now we have taken on third case where we have this multi-stage contact current extractors. So we are going to take an example for each cases. All right. So we take this first example, one on cross current multi stages. Okay, so we are looking for stages like this, where we have this feed, we bring in contact with the solvent, fresh solvents, we have the raffinate, sorry, we have this extract, take this raffinate, so stage 1, this is R1, E1, bring to the second stage, bring fresh amount of solvent, we have extract here, treated raffinate, R2, bring in contact with this third, again the solvent in the third stage, and we have this R3 and E3, etc. Alright, so this example is reads like this. You have 100 kg of say acetic acid, 100 kg of a solution in water which contains acetic acid as a solute, which is 30% weight by weight. So 100 kg of solution containing acetic acid in water, and we have been asked to extract this acetic acid using a solvent, let's say ether. Right. So here acetic acid is now your C, water the solvent, it's B, it's water is a feed here, so it's A, and the ether, which is solvent, is now B, or we also use sometime S. So the problem reads that we have to do it 3 times. So notice the difference here when we have this, when we draw the stages like this, it's a continuous process. So this F is kg per hour. So we say that its feed is going to be treated in 3 stages. Here the problem says that the feed amount of feed is given 100 kg, which is to be treated 3 times. So it's like one is you choose a stage, you bring F, contact with S. So now we have extract and raffinate. You have a settling tank, the two are in equilibrium. Now all it means that you take this E and raffinate, remove this extract, and take this raffinate, bring it back to the same stage, and bring in contact with the S the second time. So first time, second time, third time, it's like a batch operations. Here it's a flow experiments or dynamic experiment. All right, but the treatment, mathematical treatment will be the same. 1, 2, 3, they denote the stages, and you can also think that 1, 2, 3 they denote 3 times. So in other words, the first time whatever we have taken this raffinate, again you're treating it with the S in the same stage. All right. So whether it's a 3 times or 3 stages, or whether we have the total amount given as 100 kg or 100 kg per hour, you have the same treatment. All right. So the equilibrium data are given as following. So we have water and we have ether. So you can make out this is your raffinate phase R, and this ether, which is solvent, is your extract phase. And here we have been given all weight percent of acid, which is C. Then we have water, which is A, ether, which is B. So the problem statement or the data would be given in terms of acid, water, ether, and we have to identify. So this is a solute, we put C, water, it's a feed, so we put it as an A, ether is a solvent, so we put it as B. Similarly, we have acetic acid again, we have A, water, and we have B as a solvent in this extract phase. So 2 phases, raffinated extract, and we have been given the data like this: A, acetic acid, C, A, B. And data, for example, we can write down a few of them: 0.69, 98.1, 1.2. So this is the raffinate phase, large amount of solvent, we have some solute here and some amount of solvent as well. We have 0.18, 0.5, 99, and these 2 phases are in equilibrium. All right, so from here, if this is X, 0.69, this is our Y. Okay, so we require a Y-X diagram as well. So you have to identify very carefully. And similarly, here we have 1.40. This is 97.1. We have 1.5. This is 0.37, 0.7, 98.9. Any physical handbook or thermodynamics, or if you do the Google search and type for this, tertiary diagram for this water ether system with acetic acid, you should be able to locate such type of information. Similarly, here we have 36.7, then we have 46.4, 58.9, 4.4, 37.1, we have 16.5, and similarly some more data here which we skipped: 21.6, 6.9, 71.5, 36.2, 15.1, 48.7. Such type of thermodynamic data you are supposed to avail yourself. You can go through some of the thermodynamic handbook or Trebol, McAbee Smith, or the book by Datta. These information, this is a very common combinations of three species: acetic acid, water, and ether. All right. Now in this problem, it's given that we have to use 3 stages or 3 times. All right. We discussed that they have the same meaning. So our mathematical treatment for this type of problem is similar, and we have to use 40 kg of solvent. So this is 40 kg of solvent, or we can say that this is solvent flow rate is 40 kg per hour. So which means if you are talking of this flow rate, then the feed is 100 kg per hour, or if it's a batch operation, then this is just 100 kg. We have the same situations. All right. So now all we do, we first draw this equilibrium diagram, but notice here that our feed was given as 30%. All right, weight by weight, and look at y versus x diagram. The extract composition of the solute is smaller than this the solute concentration in the raffinate. That means we can stop, or we can plot only till here where the feed composition is 30%. You must understand that we don't require the data beyond this, because feed composition is 30%, so solute concentration increases 37.7%, so maximum is 37.7 here. We can take this data here, and we also realize since that y is smaller than x, so if we choose only these data here, we should be able to solve the problem. Okay, and we have been asked to find out what is the raffinate concentrations, or find out the composition of all streams. Okay, so we plot, as we said, A, B, so this is the weight fraction of ether, and all we have to do is to only go till 0.3. So we have this equilibrium diagram like this. We don't need, so this would be 1 here, this is 0 here. We don't need any data beyond this, because all the tie lines are slope or downward. So this scale from 0 to 0.3 is good enough. So this is also very important that we realize that rest of the data we don't need, so that we can expand our scale and we can work in this range. Now the feed first stage 0.3, it's a pure solvent. So this is 1 here, we connect, so we are mixing it first stage, and we mix and then we settle. So knowing the amount of this 0.3 amount of the solvent, we can write A. So let's say for the feed added, solvent added here, it gives us R1 and E1, raffinate and extract phase, they are in equilibrium. We can also write A XF plus B YS as R1 XR plus E1 Y. And its ideal stage XR and YE, they are in equilibrium. All right. So this gives us M mixing, and this gives us mix composition XM. In other words, knowing these two graphically, suppose we locate M1 like this. So we know this compositions here and here. Here we have plotted X versus X and Y versus weight fraction of ether here. So we can solve mathematically, or we can solve graphically. We have 1, 2, 3, 4. These are all known, given to us. X, R, and Y not given to us, but we know they are in equilibrium, right? So 2 unknowns, 2 equations. we have to calculate this xm. Once we know xm, let's calculate xm1, which is, put the number here, 100 for A, feed is 0.3, solvent amount is 40, either 40 kg per hour or 100 kg per hour or just 100 kg and 40 kg into 1. Solvent is pure, 100 plus 40, 140, get this 0.21. So this location here is, say, let's say 0.21. All we have to find out a tie line which passes through this. So we have this extract E1, and here we have this raffinate R1. All right. So if you know this XM1, again you can do the same exercise now for R1 plus E1 and XR plus E1. I leave this as an exercise. You should be able to obtain R1 as 96.4 and E1 as 43.6 to make it total as 140 kg. So this raffinate R1 and E1, we have the amount from the equilibrium curve. You can read this, should be 0.258, or you can also calculate, right? And this E1 is 0.117. Now take this raffinate and connect this to B. So we have the stage 2. So this is stage 1, and now we are talking of stage 2. For the stage 2 also we have the similar equations. First you are supposed to find out what is M2. So what is the second mixture compositions, and then find a tie line which passes through this MT to give you R2 and to give E2. Right. So you can do this exercise yourself. Let's just plot here the 3 stages compositions. So we have A, let's say this is B, 0, 1.0, this is 0.3. We have this equilibrium curve like this. We connected first stage. We find M mixing, M1 here, let's say. Find a tie line. So this one is R1, this one is E1. Connect this R1 to this stage here again. Find the new M2 point. Find another tie line. Need not be parallel. E2 and R2. Or mathematically you can solve. You know this amount of R1. You know this B. You know the compositions here. Find the new M2 and find the new tie line which passes through this M2 here. In this case, we can show that your XM2 will be equal to 0.18, and the amount of raffinate and extract will be 90.1. Extract E2 will be 46.3. If you add these two, this should be the amount of 136.4 kg, the amount of raffinate which we started with. All right. So this is the raffinate and E1, E2 here, and this compositions here. If you note down, this composition would be 0.095, and here this raffinate would be 0.227. All right. So again, connect this R2 to this feed phase solvent. Find the new M3 and find this tie line. This time, this point should read as 0.2, and this E3 should read as 0.078. Okay. In this case also you can note down the third stage. XM3 will again be equal to, say, 90.1, that's what we had, into 0.227. So this is 0.227 here, plus we have fresh amount of solvent 40 into 1, divided by 90.1 plus 40, 130.1. This will give us 0.1572. So we locate this coordinate. Again, we find the tie line which crosses through M3 to obtain this 0.2 here, and we locate this 0.078, and then again one can find raffinate R3 as 84.4 and extract amount as 45.7. Alright. In other case, if we summarize here, we were given a feed which has a composition of 0.3. Alright, so this was the solid acetic acid present in this. We had the amount of feed amount was 100 kg. 3 stages we had brought down this level to 0.2 by using 3 times. So we have the amount of solvent we were using S or B. This was 40 kg. Alright, so the total amount of solvent we had 120 kg. Alright, we brought down the concentration from 0.3 to 0.2, and the last raffinate concentration, molar flow rates R3 was 84.4. That means the acid content in the treated stream or the raffinate stream would be 84.4 multiplied by 0.2, 16.88. Right, so much acid in this. So here on this example, what we have done, that we have just 3 stages, or we are doing it 3 times for the batch experiment. Every time we bring the amount of the solvent and we reduce the concentration of acetic acid from 0.3 to 0.2. Now one can also come do one more exercise here. Suppose we use only 1 stage. Alright, so instead of using 3 stages and equal amount of solvents, 40 kg each, the question is that if you use only 1 stage, how much amount of solvent is required to bring down the concentration levels from 0.3 to 0.2. So though we want to fix the composition of the feed and the raffinate, treated raffinate, which we have in the from 3rd stage at 0.2, and how much is the amount of solvent required. This will tell us whether single stage is beneficial or the 3 stages, alright, for the given amount of solvent, or how much is the amount of solvent is required if we do the treatment in 1 stage instead of 3 stages. Alright, so this very quickly, suppose we use only 1 stage, that means we can redraw the equilibrium curve here, or we can work on the same equilibrium curve. We have this A, and let's say this is B here, right, and this point was 0.3. So what after 3rd stage we had this compositions at 0.2. So this was the composition of the raffinate R3 at 0.2. Now we are supposed to use only 1 stage, and the question is that we want to bring down the level from 0.3 to 0.2. So all we do, we just add 1 stage here. Okay, amount of solvent is not known to us, so to find out how much amount of solvent we require, right, this is 1 here fresh solvent, so that the treated stream, this raffinate, contains 0.2. So now again we have this R stage, it's an equilibrium with the stage, with the extract phase from that stage. So again here we have to do this exercise. We find that tie line which connects this raffinate concentration at 0.2. So if you do this, you have the equilibrium Y versus X diagram from the same informations what we had in the beginning of this lecture, in the beginning of this exercise. You have to look for 0.2 here, right, corresponding to this. Find out what is composition in the Y phase. So if this is 0.2 here, you find this tie line, you will see that this corresponds to 0.078. So actually here this is now X, and this is your Y. Alright, so knowing this 0.3, the amount of what amount of solvent is required, so that we get only 0.2, find that tie line which goes through this. You will see that this So reading here, this would be around 0.12. Okay, so if we know this xm, again we have a similar exercise. 100 kg solvent, we add 100 kg of feed. Now we add this amount of solvent B. We have R plus E, raffinate and extract, and we have 100 into 0.3 mixing rule plus B into 1, and we have this R, raffinate, into 0.2 here, plus E into Y. So this is 0.078. This is your now mixing M here, and similarly we have this M into XM, where XM is 0.12. Okay, so if we do this small calculations, we can find that the amount of solvent here is 150 kg. So this example test, which is if you have 3 stages, we required 120 kg, and if you have just one stage, for the same amount of concentration levels going from 0.3 to 0.2, we required a large amount, 150 kg. All right. So this example we have chosen for this lecture for cross current 3 stages, where we added the fresh amount of solvent at every stage, and we were asked to identify on different compositions. We drew the equilibrium curve. Graphically, we said that we can solve graphically as well as we can solve mathematically. Okay, but we have to plot both y versus x diagram, equilibrium, and we have to draw this rectangular coordinates, amount of solvent, fraction of the solvent, and y versus x. Start with the first stage, add f and f, find the mixing rule xm. You can solve graphically, you can solve mathematically, find the new tie lines, second stage, third stage, and the last question was put up. If you use just one stage, what is the amount of solvent? And we showed that if you use just one solvent for the same level, same reductions in the quality of the feed, we require more amount of solvent, 150 kg. Now that's the end of today's lecture. The second lecture, when we take up, we will take an example on multi-stage counter current stages. Okay, ठीक है.